So we're asked to calculate Young's modulus for the material of the bar shown below. The bar has an initial length of 400 millimeters and is measured to extend by 0.22 millimeters under the tensile load of 75 kilonewtons. When the force is released, the bar returns to the original length. The bar has the rectangular cross-section shown at right. Okay, so the first thing I guess we should identify is the fact that this is really telling us that when we deform this bar, it's only within the elastic section of the curve. So if we draw an example stress-strain curve, it might look something like this. We know that this transition from the linear to the nonlinear section occurs at the yields point. And up to that point, it's called elastic, and beyond it, it's plastic. So when it tells us that when the force is released, the bar returns to the original length, it's telling us that we're in the plastic zone and not in the, it's telling us we're in the elastic zone and not the plastic zone, because any deformation we cause in the elastic zone is recoverable, so we go back to the original length. If we're in the plastic zone, we end up permanently deforming our material. So when we go ahead and calculate our stress in this bar and our strain, we're going to know that we're landing somewhere in the elastic region of this curve, and I'm just going to mark it as an example here. So let's go ahead and calculate the stress first of all. We know it's equal to the force divided by the cross-sectional area. So we need to put in the internal force, which is going to be this 75,000 in newtons, and the cross-sectional area is, we're given it here. Now I'm going to do it in millimeters squared, so 20 by 25. And because we've got newtons divided by millimeters squared here, our stress should come out in megapascals, and in fact it becomes 150. Now, just before I move on to calculating strain, just want to quickly mention about this force here of 75,000. Now, this is the internal force within our member. And I know that there's a force on like either end of our bar here, but if you're ever in doubt and you want to calculate the normal force, you don't add them together. You want the force inside the bar. So if this is our free body diagram, what we can do is take a cut through the material, and we're going to have it in two pieces. We can take either the left hand side or the right hand side. If I take the left, I'm going to redraw it. And our internal force is what I'm going to replace at the cut, and I'm going to call it F. And we know that for equilibrium, the sum of the forces have to be 0, so this force F has to be equal to 75 kilonewtons, which is the one that we put in here, same as 75,000 in newtons. So don't ever add these together. What you want to put in terms of F here is the internal axial force within the bar, which will be equal to whatever's applied on either end, and only one of them. Alright, so now what we want to do is calculate the strain that this stress corresponds to. So we have our equation for strain, where it's equal to the change in length divided by the original length. Now we were told that it changed by 0.22 millimeters under that load. And the original length is this 400 here. So both of these are in millimeters, which means the units are going to cancel out, and strain becomes a unitless measure, and that's the value that we get out for it. So we can mark these on the diagram. So this here is going to be 150 megapascals, and this point here is going to be at 0.00055. So now we just need to calculate the gradient through this line. We also know that the plot starts at 0, 0. So it's just a case of applying your equation for Young's modulus, which is that it's equal to the change in stress divided by the change in strain. So the change in stress between this point and the bottom down here is going to be 150 megapascals. I'll put the -0 in for the change, and along the x-axis, the change is going to be 0.00055, and we end up with an answer of 272727. This answer is going to come out in megapascals because that's the unit that we used for stress. If we wanted to convert this into gigapascals, we could round it as well, it's going to become 273 gigapascals. So that's the Young's modulus of this material. So that's all there is for that question, and see you in the other examples.